All right, so finally we come to the manual conversions. So in order to fully understand floating point, to really kind of have a sense for how it works, it really helps to do some conversions manually. This is unfortunately a bit tedious, some would say quite tedious. It's pretty error prone, but there are some general guidelines that can help for it to go faster. And I will say that the more you practice, the faster and better you will get at it. And so I encourage you to make sure you set aside enough time to practice these things until you're at least relatively comfortable with doing these conversions. There's a utility that I wrote that is available online. There should be a link in the class resources, but here's the GitHub repository for it. This will generate test problems for you. So you can compile it using the instructions there, and then if you run it and give it 2 integer numbers, it will generate all possible positive floating point numbers using that representation, where the first number is the number of bits for the exponent, and the second is the number of bits for the significand. So it'll give you output that looks like this. So if we said, for instance, that we wanted 4 bits for the exponent and 3 bits for the significand, it would give us all possible 8-bit values where we have 1 sign bit, 4 exponent bits, and 3 significand bits. And so it'll give us this gigantic dump of output, and then you can go through and pick out the one that you, or just randomly pick one that you want to test yourself with, and then either start on the left-hand side with the binary and convert that to the decimal or the decimal value that's being represented, or start with the decimal value on the right and convert that into the encoded floating point value in binary. The textbook's technique for this involves a bunch of these intermediate quantities, and if that technique works for you, that's great. Please feel free to just use that technique. So you should take a look at that in the textbook. Some people find a slightly different perspective to be a little bit easier to work with. So here is a slightly different way of thinking about these things. So these are kind of procedures to follow when doing a conversion. So if you're converting from the binary floating point into the value that's being stored, or the decimal value, there's really kind of 3 pieces that you need before you can calculate the final value. So you need to pull out the sign bit, and if the sign bit is set, then your value is negative, otherwise it's going to be positive. You need to recover the exponent value. So if your exponent is all zeros, remember this is denormalized, in which case the actual value is 1 minus bias, which is kind of an exception to the rule. If it's all 1, remember we have a nan unless all of your fractional bits are 0, in which case it's infinity. And in this case, we're done, right? So if we have an exponent that's all 1s, then we've hit a special case, and we just need to determine whether it's infinity or a nan, and then that's it. There's no actual decimal value. Otherwise, we have a regular normalized number, and so we can calculate the true exponent as being the stored exponent minus the bias, which is how the bias encoding works. Then we have to recover the significand. So if we are normalized, then we'll just need to calculate, we need to add up all the powers of 2 from the fractional part and then add 1. If it's denormalized, then we don't need to add that extra 1. We could also just use these formulas that are here, where you take the fractional value and you convert it to a number, and then you divide by the or I guess sort of the smallest value of 2, or power of 2. So you'll divide by the largest, by the power of 2 that corresponds to the number of bits you have, and that's equivalent to multiplying by a negative number of a negative power of 2. So once you have the sign bit, the exponent, and the significand recovered in their decimal formats, then you can just calculate the multiplication of the result, and then you have the final number in decimal form. If you're converting the other way, so going from decimal to floating point, here's the procedure that you would follow. And this is for normalized numbers only. We're not going to ask you to convert denormalized numbers from decimal into floating point. We may ask you to go the other way, but it's just a little too tedious, and there's not much learning value in learning how to convert decimal numbers to denormalized floating point numbers. So For regular normal numbers, you will want to, first of all, take the decimal number that you're trying to convert and convert it to binary. So you'll have a binary fractional number, and you can go ahead and set the sign bit at this point because, of course, you know whether it's a positive or negative number. Then you need to normalize that number, so you'll need to slide or shift the binary point to the left or the right, and you need to keep track of how many places you shift left. If you shift right, then it'll be a negative number. And then once you've done that normalization, the bits to the right of the binary point, those are the significand, and you can just put those directly into the floating point the binary floating point representation. If you need to pad with zeros on the right, you can, and you should. But you should sort of align the numbers to the left-hand side of the significand field. If there aren't enough bits in the significand field to store the entire fraction, then the value is rounded and you aren't going to be able to exactly represent the number. Once you sort of have the significand, the last piece is the exponent. So you need to go back and remember how many places you shifted the number in order to normalize it. Once you have that shift offset, we will need to encode that shift offset using the bias representation, which is basically just adding the bias. So we subtracted the bias in order to go the other way, and so it should make sense that we add the bias when going this direction. If the exponent, and then of course you need to convert it to binary. And if you cannot represent the exponent given the number of exponent bits that you have, then you underflow to 0 or you overflow to infinity. So here's an example worked out for 2.75 in decimal, and we are assuming that we have a 4-bit exponent and a 3-bit fraction. Again, the context is really important, right? You can't do either of these processes if you don't know how many bits you have for each part of the number. And in fact, you could get wildly differing results if you're using different floating point layouts. So here we start with 2.75 in decimal. We convert it to binary. And so we get this. We normalize it by shifting to the left 1. So that means that we have a shift offset of 1. Once we've normalized it, we have those bits which we can take and move over into the fractional part of the number. We don't have to do any padding here because the number of bits that we had in the number are the number of bits, so we don't have padding. And we also don't have any rounding in this one. We can represent the value exactly. And then we take the shift offset, we add the bias. Again, here's the formula for the bias if it's not given to you in the problem. And then we take that number and we encode it in binary, and that's the result. So again, this is all a little tedious, so you should make sure that you set aside time to practice this. The lab will have a bunch of examples, so you'll get some practice there. But again, this is something that you really kind of just have to sit down and work through some examples before you really start to feel comfortable with it. But it does get a little more. It does get easier the more you practice it, and you do really start to get a sense for how these numbers work after you do a few examples of them. So I strongly urge you to make sure that you spend the time to make sure that you achieve that level of comfort with this.